Hello, my name is Claudia Rivera. I'm going to present you this work where we synthesize Upconversion nanoparticles of yttrium vanadate with erbium and ytterbium. This work is being carried out at Centro Universitario de Ciencias Exactas y Ingenierías of the University of Guadalajara. Well, typically ceramic oxide nanoparticles such as yttrium vanadate are doped with rare ions to exhibit photoluminescence. That means that, for example, this powder could emit light, but without the addition of these ions, the emission usually doesn't occur. So it is very important to have a good control of the amount of the dopant concentration because, for example, with a high concentration of these ions, the emission is quenched. This kind of luminescent materials can be used in many devices, for example, in electronics, in many types of screens. But they have recently been employed to create biodetectors in cellular tissues. For example, imagine that these nanoparticles could be specifically placed within cancerous cells. The light emission would allow us to visualize their location and also to differentiate between a disease or a healthy cell. This application will provide an advantage in the early detection of diseases, for example, in cancer. There are already some biodetectors based on fluorescent nanoparticles, and the most common method for obtaining light emission involves excitation with ultraviolet light. However, as is well known, ultraviolet light can be harmful to cellular tissues, making such sources less desirable for biological applications, especially in vivo experiments. Additionally, some tissues may exhibit excessive autofluorescence. That means that, for example, if you have a green emission from your nanoparticles, also you will have a green emission for your tissue, and you can also lose the nanoparticle. So this kind of emission from ultraviolet light is not good, and we need to find another kind of excitation, for example, using infrared light. To address this problem, the ceramic matrix of yttrium vanadate can be doped with erbium and ytterbium ions. As we said, we need to control the quantity of these ions. This combination allows the matrix to absorb infrared light instead of ultraviolet light. That means that we are creating a upconversion luminescent mechanism. The synthesis of these materials was straightforward, relying on chemical co-precipitation to obtain a white precipitate. We vary the concentration of dopants to achieve a high-intensity green emission. Diffraction patterns show that the nanoparticles right only at room temperature already have the well-formed crystalline phase of yttrium vanadate. However, in photoluminescence, it was found that without calcination, there was no green emission through a conversion mechanism. That means that we need to perfect the structure of the yttrium vanadate to generate the electronic transition for conversion. So we need to calcinate even to 1,000 degrees. Also, we show here that we found a specific stoichiometry where the emission has a higher intensity from the other stoichiometries studied. Another characteristic we noticed was that the emitted light depended on the washing condition. For example, if we clean the sample with distilled water, the emission intensity decreased slightly compared to when we use ethanol. X-ray diffraction indicate that the yttrium vanadate was formed in this sample, Also remember that these samples were calcinated at 1,000 of degrees. Finally, using a microscopy of high resolution, we observe that the cleaning methodology is very important because in this stage we could create some kind of pores in the nanoparticles. For example, using distilled water, we can see some kind of internal pores on the nanoparticles that we don't have using ethanol. This kind of pores maybe are the reason why this sample has less intensity than this. In conclusion, this work highlights the sensitivity of yttrium vanadate or conversion nanoparticles to synthesis methodologies. We can say that we found a good emission intensity for these conversion nanoparticles. So the next step could be functionalize the surface of these nanoparticles to create a good biodetector for cancer cells. Finally, I want to thank to the collaborators who made this work possible, especially to Dra. Verónica Rodríguez Bentancur and to CONACYT for the postdoctoral grant, and want also to thank to the Universidad de Guadalajara, where this project is being carried out. I hope you enjoyed our work. For any question, please feel free to contact me. Thank you.